We want to look at something related to momentum, and that is the center of mass. The position of the center of mass of a system is the weighted average position of the system's mass. By weighted average, what we mean is if we have two masses like this, we take their respective positions, in this case x1 and x2, and we weight the masses down by their position and divide that by the total mass of the system to get the center of mass, the one location that represents the system. In terms of a mathematical equation, our center of mass is equal to mass 1, position 1, plus mass 2, position 2, divided by the total mass, mass 1 plus mass 2, of the system. And we can think of these as weighted positions, add together, and all that is equal to the total mass, m1 plus m2, times this one location, the center of mass. Now, in using this formula, these positions could be positive or negative. We're anywhere on this coordinate system, this Cartesian coordinate system, and the values of x could be positive or negative. That's fine. We're just trying to find the location on this coordinate system of the center of mass. You may ask, well, Dr. Golben, this is a perfectly beautiful equation. We love it. But what is it doing in a chapter on momentum? And I would say that's a great question. Well, take a look at this equation. This is the conservation of momentum equation for a perfectly inelastic collision. Mass 1 v1 initial plus mass 2 v2 initial equals mass 1 plus mass 2 common v final. And what we're saying here is our initial momentum equals our final momentum, but our initial momentum was all these masses doing their own different velocities, and then the final momentum, where they stick together and move as a common mass with one velocity, it's really the whole system moving as one mass with one velocity after the collision. So the momentum of all these things going on before is equal to the whole system moving with one common velocity. Note how similar this looks to our center of mass equation. We have mass 1, position 1, mass 2, position 2 is equal to the total mass times the center of mass. The only difference between these equations is one is moving and the other one is not. For the center of mass, you have a location that represents the whole system as one total mass, and for perfectly inelastic, it's all moving by one mass moving with one common velocity. So the mathematics are very similar, and the only difference is one is moving and the other one is not. Let's try out the center of mass equation on a problem. Here we have two masses, 1 kilogram and 2 kilograms respectively, and they're located 3 meters apart. Let's find the center of mass. We're going to put one of them at the origin and the other one at x equal 3. And if we put in our numbers, we would have 1 kilogram, location x is 0, plus 2 kilograms, location x is 3, over the total mass of the system, 1 plus 2. So we'll have 6 divided by 3, or the center of mass is at x equal to 2 meters. We can see that this location is actually closer to the 2 kilogram mass than it is to the 1 kilogram mass. That should be expected because the 2 kilogram mass is larger. And it's actually a 1 to 2 ratio. In other words, since our masses are 2 to 1, our location is 1 to 2 in terms of the location of the center of mass related to these respective masses. That might be something to keep in mind. In general, if we had a system of particles in 3 dimensions, we might have a whole bunch of masses out there, all with their 3-dimensional coordinates, x, y, and z. How do we solve the center of mass for that kind of problem? Well, what we'd like to do is break it up into 3 one-dimensional problems. We can find the center of mass in the x direction, the center of mass in the y direction, and the center of mass in the z direction. and then that would be our x, y, and z for that location of the center of mass. So we just break it up into three components. Center of mass x, every mass multiplied by its x position, add together, divide by the total mass of the system. Center of mass y, same idea. Every mass weighted down by its own position in the y direction, divide by the total mass, and in the z direction as well. The weighted average of all the masses divided by the total mass. Let's try this out. A system consists of three particles located at the corners of a right triangle. Find the center of mass of this system. We have three particles, 2 kilograms, 1 kilogram, and 4 kilograms. It's all in the x, y plane, so z is equal to 0 for all three, so our z center of mass is 0. What about our x center of mass? Each mass multiplied by its x position, add together, divide by the total mass of the system. So we have mass 1, which is 2, located at x equal 1. We have mass 2, which is 1, located at x equal 3. And then we have mass m3, which is 4 kilograms, located also at x equal 3. So 2 times 1 plus 1 times 3 plus 4 times 3 over the total mass, which is 7 kilograms. That's going to be 17 divided by 7, or 2.43. So somewhere on this line, where x is equal to 2.43, is our center of mass. Do the same thing for the y direction. Multiply each mass by its y coordinate. So we have 2 kilograms times 0, 1 kilogram times 0, 4 kilograms times y equal to 2. That's going to give us 8 in the numerator. Over the total mass, 2 plus 1 plus 4, that's 8/7, or 1.14. So somewhere at y equal to 1.14 is the center of mass, and where those two lines intersect, that is indeed the location of our center of mass. At x equal to 2.43, y equal to 1.14. Note, if you look in the x direction, that you have 5 kilograms over here and 2 kilograms over here, and we are closer, much closer to the 5 kilograms than we are to the 2 kilograms. Likewise, in the y direction, we have 4 kilograms up here and 3 kilograms down here, and we're a little bit closer at 1.14, a little bit closer to the 4 kilograms than we are to the 3 kilograms. So we can think of that weighted position in that sense. What would happen, though, if we had a continuous mass made up of many pieces of infinitesimal size? We can sum up the position times the mass for every little bit of mass on this uniform continuous piece of mass, sum up all those contributions, weighted contributions, divide by the total mass, and we would get the center of mass of that continuous distribution. Now these delta m's, delta m sub i's, are infinitesimal masses. So if we had a summation of a bunch of infinitesimal masses, the delta becomes an integral. So we end up having r dm, or dm is our infinitesimal mass throughout this object. And then divide that by the total mass of the system. Let's try this out. Let's find the center of mass of a rod. We have a rod like this. This is like a meter stick. We want to find the location of the center of mass. Now I know that this rod has a total mass m and a length l. And so I could say its mass per length is m divided by l, which is a constant. And I'll designate that by lambda. Equivalently, I could say that this is the infinitesimal mass dm divided by the infinitesimal distance dx. That should also be lambda as well. So I can say that dm then is equal to lambda, a constant, times dx. We want our center of mass, so that's going to be 1 over the total mass. Integration of our location, x, times dm. Integrate it over the whole length of this rod from 0 to L. But dm is equal to lambda dx, and lambda is a constant. I can always take a constant out of the integral. So I'm going to pull that out of the integral. I'm going to have the integral of x dx. So I have lambda divided by m. The integral of x dx, you know from calculus, is 1/2 x squared. And we will evaluate that from 0 to the length of the rod, 0 to L. So we have 1 over m. We have lambda, which is mass divided by length. And then we have 1/2 L squared minus 0. The m's cancel out. And one of the L's cancel out. And we are left that our center of mass is located at L divided by 2. Well, you were saying, well, I could have told you that. If you had a length of rod like this, the center of mass is going to be, and if it's continuous, the center of mass is going to be right in the middle of the rod. But this is the way we prove it mathematically. It's right in the middle for a continuous mass. What about this problem? A circular hole of diameter A is cut out of a uniform square of sheet metal having sides 2A. What is the center of mass for the remaining portion? Well, we're going to define the mass per area as being sigma, and to deal with this problem, we're actually going to make it simpler rather than try to integrate over this hole, which might be very, very difficult. We're going to treat this as two objects. We're going to have a full square of sheet metal whose center of mass should be right in the center of that square. And then we're going to have a hole, a circular hole, whose center of mass would be right in the center of the hole. We'll treat the full sheet metal as a positive mass, and we'll treat the hole as a negative mass. If we find the center of mass of those two objects, we will find the center of mass of this combined object. Sounds good. So we'll define the surface density of mass per area as being sigma. If we look at the square, the location of its center of mass is at x equal a, because the edge is 2a. And the mass of the square is going to be its surface density, mass per area, times the total area of the square. It's going to be 2a times 2a, which is 4a squared, times sigma. And that will give us the mass of this square. So we have the location of the square and the mass of the square for our first object. Do the same thing for the hole. If I look over here, the location of the middle of the hole is at a plus a divided by 2, or 3/2 a. And the mass of the hole will be the density, mass per area sigma, times the area of the hole, pi times the radius squared. The radius is a divided by 2, so it's going to be pi times a divided by 2 squared. And it is a hole, so it's going to be a negative mass. So we have negative sigma pi a divided by 2 squared. So we have the location and the mass of the second object, which is the hole. If we find the center of mass of these two objects, we would find the location of the center of mass of the combined effect. So we're just going to use our summation, one mass times location plus the other mass times location over the total mass of the system. So we have the square, its mass, sigma 2a squared times its location, which is a, plus the whole, sigma pi a divided by 2 squared, times its location 3/2 a, over the mass of the square, plus the mass of the whole. I have sigma in both terms in the numerator. I have sigma in both terms in the denominator. If I divide top and bottom by sigma, I get rid of sigma. I end up with this. 4a cubed minus 3/8 pi a cubed is divided by 4a squared minus 1/4 pi a squared. If I divide top and bottom by a squared, I get rid of a squared in the denominator, and I'm left with an a in the numerator. And this is equal to 0.878a. So that's my answer. How about that? So if I had the full square to begin with, its location of the center of mass would be right in the center at A. Since I put the hole in there, the center of mass shifted over a little bit to 0.878 A. This object is symmetric in terms of x versus y, so the location of the center of mass in the y direction will be the same as the center of mass in the x direction. So they both will be at 0.878 A. If I found the intersection of those locations, x and y, there would be my center of mass. Look at this though. If I took the same object and I suspended it from one corner and let it, rotate back and forth until it finally found, an equilibrium and stopped. When that happens, that means gravity would have no more torque on the rotation of that object, and hence the force of gravity must be vertical, acting on the center of mass of that object. So if you found it to rest in this position, the center of mass would have to be on the vertical line from the pivot down. So if I drew a line straight down, somewhere along that line, somewhere along this red line, the center of mass will be located somewhere on that line. Fine. Well, let's suspend the same object from a different corner. If we do that, it's going to rotate until it finally stops. It's going to be a little bit skewed in the way it looks, but from the pivot straight down, somewhere along that line should be the center of mass. So if I were to draw that line, somewhere on that blue line should be the center of mass. If I combine that with the red line, where the two intersect, is my center of mass. That would be a mechanical way to quickly find the center of mass of an object. Just suspending it, draw a vertical line, suspend it again, draw a vertical line, and where the two intersect, that is my center of mass. Try your hand at some of the problems. Take a look at the edu-creation examples, and we will have a separate short lecture to look at the rest of this chapter.